got a lot to do today. We call this method a shrinkage method. Do you remember the other time when I introduced it to variable selection? One of the approach in the variable selection is we have an approach that can shrink the regression coefficient to 0. And we have an approach that will not shrink that to 0. Okay. But what that approach is basically, what our approach is going to do is you actually going to make the predictor variable in the model not to be significant. Now we're gonna look at that. Okay. In the outline, improve, we're trying to improve on ordinary least squared. Then we'll talk about bias versus variance. Then we're going to talk about the lasso and the regularization. Regularization is more or less like we're introducing shrinkage. Now let's look at the improving on ordinary least square. Let me tell you this. We use ordinary least square when we are assuming linear relationship. But if there's a violation, what happen? We cannot trust that anymore. Okay, now improving, how can we improve on ordinary least squared? We can do subset selection. I walked you through that last time. We can do shrinkage. The shrinkage is what we want to do now. We can do dimensionality reduction that we call principal component analysis that we've done in this class. And I told you the other time, the issue with the principal component analysis is that you're basically going to generate a new set of principal components, even though each of them is going to be made up of the original one. But there's going to be an interpretation issue because you're no longer working with the original one. Now we want to talk about shrinkage now. But let me tell you this. You remember when I started this course, I actually walk you through 5 tensions, right? Do you remember? 5 tensions that distinguish between explaining and predicting. You have to decide on what you want to do. Do you want to explain or do you want to predict? When you talk about bias and variance, bias remains the worst enemy of every statistician, every sociologist, every psychologist, every economist, everybody in the scientific community. And because of that, when you try to increase, because one of the ways to reduce bias is to consider more predictor, right? But what happened when you had more predictor in your model, even though you're basically going to reduce bias, but that will lead to another problem. You're going to increase the variance. And when the variance goes up, what happens? Then it means you cannot, your model is just going to perform very well with training sets, but poorly with test set. Sorry, with test set. Does that make sense? Okay. Now, what do we want in the world? In the scientific, in the statistical world, what is the ID? What is the best ID situation? When we have a low bias and low variance. That is the first one. Can you see that, right? That's a good one, right? That's the best one, right? That's the best scenario. But that very scenario will be difficult to match in this stochastic world. Now, take a look at the second one. That one is talking about low bias, high variance. Low bias, high variance is the scenario that I just talked about. You get so many predictor variable. You have a low bias, but you have high variance. That's a problem. And take a look at the other one. Okay, high bias. Okay, with low variance. High bias with low variance is more or less like, look at the assignment that I gave you. Let us assume that more than one predictor affect a response. If you only consider just one predictor, what happened? Then your model will underestimate. Does that make sense? And that is the model is going to have high bias, because instead of you to consider a lot of predators, you only consider just one, right? Even though it's going to have low variance, but what about high bias? Now, the last one here, oh my God, that's a double tragedy. High bias and high variance. Okay, now, this is the interpretation of low bias. The average prediction is very close to the target value. Of course, you remember in statistical analysis, where we normally say, if I have an estimator, theta cap, and this is a parameter, then the theta cap is unbiased if this is equal to that. The same way we normally say the sample mean is unbiased of the population mean. That is what we mean by unbiased, because one is one of the property of an estimator. So that's what low bias mean. But high bias means your prediction is differ too much from the actual value. We actually want to minimize the distance between what your model predicts and what actually happened in reality. You know that? And low variance data point are compact and they do not vary from the mean. And high bias means a scattered data point with huge variation from the mean value and other data point. These are kind of situations that we face in a stochastic world. Now, to make a good fit, there's going to be a trade-off. You know why trade-off? If you focus on one, if you focus on bias, you will have issue with variance. If you focus more on variance, you will have issue with bias. Then we basically need to, look for a way to be in the middle. Okay? So we need to have a correct balance. That's what I mean of the situation. Does that make sense to everyone? Okay. Now, what do we now need to do this? We need a regularization. Okay? And what do we mean by regularization? Okay, it's a way to improve our model to work on the unseen data. Ignoring less important features. Because when you consider so many variables in your model, even though they're going to perform greatly with the training set, but it will perform poorly with the unseen data. And what we're trying to do with the regularization now is a way to curate the balance to make sure that the model is improved upon and the model can actually work greatly with unseen data. But let me tell you this, we can never eat our cake and have it. You know that, right? So if you basically want that to happen, then it means you should look for a way, to ignore the less important features. So regularization minimizes the validation loss. And when you minimize the validation loss, then you are making an attempt to improve on the accuracy of your model. How does regularization does that? We need to regularize to avoid overfitting. I'm going to say that again. We need to regularize to avoid overfitting. We don't want overparameterization. I'm going to say that again, overparameterization in a situation where you got a lot of variables in your model. There's going to be so many parameters to estimate. Does that make sense? And that is the reason why by regularization, okay, we had a penalty, okay, to the model. Okay, and the penalty that we're going to have with the model, we have high variance. And that in a way we shrink the coefficient to 0. Take a look at that. Okay. Now, when we talk about shrinkage, of course, the idea behind shrinkage is help us to reduce the variance and in a way increases bias. Let me tell you something. When you increase bias, That does not always result in a good variable selection. And what we're going to do is to apply a regularization approach that can actually balance the variance and the bias. What are the two methods that we use in the regularization? What are the two shrinkage methods? The lasso regression and the ridge regression. Then I basically want to welcome you into two types of regularization that we also call two shrinkage method, the lasso and the ridge. Now, in statistical analysis, don't forget, we basically want to regularize the low, we actually want to have a low bias and the low variance, that the best situation, right? And we believe that whatever regularization we want to do, we'll be able to get something very close to that. If not, it can't be exactly that. And we can use a lasso, we can use ridge. Lasso is called L1, ridge is called L2. The difference between lasso and the ridge is just like the lasso do that with an absolute time. The ridge do that with a square time. And let me tell you, the lasso will shrink the coefficient of irrelevant predator to zero. but ridge will not do that. You know what ridge is going to do? Ridge will still retain irrelevant variable in the model, except that they will not be significant. The p-value that come out with ridge will not be significant. Let's take a look at the way the ridge regression is going to be. Of course, in every regression, we want to minimize the sum of square error, right? We want to minimize the unexplained variation, right? Okay. Now, if I want to actually regularize, if I want to use a shrinkage approach, then I'm actually going to introduce something into the residual sum of square of the ordinary least square. Don't forget, what do we want to do? We want to improve on the ordinary least square. If you want to improve on the ordinary least square, then the way to improve on the ordinary least square is basically to undo, to see how you can minimize the residual sum of square associated with the ordinary least square. Now, that was why the first one, I'm giving the residual sum of square of the ordinary least squared. And I'm now introducing that of the ridge regression now. So what is the difference between the two? It is this guy here. The other part, I have a lambda summation beta j squared. That is what we introduced. But let me tell you this, introducing that. What is the function of the lambda? The lambda is going to be a tonic parameter. Okay. And the lambda will be determined from the data. If lambda equal to 0, what happened? If lambda equal to 0, for instance, you have a set of data now. And that return lambda to be 0, you know what it's telling you? Use the ordinary least square. You don't need to improve upon that. The ordinary least square is fantastic. When lambda equal to 0, oh my God, when lambda tends to infinity, what about that? When lambda tends to infinity, so that was why I said the larger lambda, the more the shrinkage. When lambda is large, then it means I need to do a lot of shrinkage. When lambda is very close to 0, I don't necessarily need shrinkage. Any question? Any question? Now, the ridge penalty is the summation beta j squared. Because if I also show you that of the lasso, there's still going to be a tonic parameter. But instead of working with a summation beta j squared, I will be talking in absolute value. Take a look at this guy now. Oh my God. If you take a look at this guy, okay, sorry, I'm still on the ridge. Let me see. Let me quickly show you if I have the, okay. I quickly want you to see the lasso one so that you can quickly see the difference. Do you see the lasso one? Instead of having the summation of beta j squared, I'm having an absolute value. I want us to think now. Let's see. I want us to think now. If I'm talking about difference between, take a look at this. 5 minus 2, 2 minus 5 If I want to look at the square, they are the same. Right? They are the same. Ridge is using that. If I want to use absolute value, is it not? They are also the same. Absolute value of this is 3. Absolute value of 3 equal absolute value of that is 3. This is lasso way. This is the ridge way. Don't forget, in the ridge, you have this guy. In the lasso, it is the absolute value now. Any question? But it is the lasso one that will shrink. The lasso one will completely eliminate irrelevant variables in the model. But the ridge one will not do that. The ridge one will still retain them, except that their p-value will be large. Any question? Any question? Okay, now going back here now, we basically want to optimize. We want to minimize that function subject to, summation bj square less or equal to s in the ridge. Okay. Now, how can shrinking towards 0 help? We're talking about lasso now, right? Now, this is what happened. I said the whole LS estimate are unbiased if the model is true, but its variance can be high when predictors are highly correlated. I told you, when there's a problem of multicollinearity. Do you know when you have a lot of variables, a lot of explanatory variables, there's possibility that some of them may be given the same statistical information? Then if they are outliers or situation where n is less than p, what is the meaning? The number of observation, we normally have something like this in big data, where the number of observation is less than the numbers of explanatory variables. Take a look at the jinx sequencing, where you have a lot of maybe 5,000 or 10,000 predictor, and the number of observation is not even up to that. In that kind of situation, of course, this shrinkage is basically going to work. Let me tell you this, according to Gauss-Markov theorem, before I can apply the ordinary least squared on data, I'm expecting the number of observations to be greater than the number of explanatory variables. I'm going to say that again. According to Gauss-Markov theorem, if I want to apply ordinary least squared, assumption is that the number of observations should be greater than the number of predictors. But a situation where the number of observation is less than the numbers of predictor, the OLS will not work great. Okay, and that is the reason why we need a penalty. The penalty will actually increase bias in a way, but it's going to bring the variance down. Does that make sense? Because why is it going to induce bias? Because it's eliminating variables. And if you have few variables in your model, there's going to be bias if you have eliminated some variables. Okay, and that was why we need to choose a tuning parameter. With the tuning parameter, we'll be able to have what I call we can balance situation between the bias and the and the variance. Now, you remember the other time when we have a multiple linear regression and I want to estimate beta, we use that guy, right? The S transpose T, S transpose Y, right? But the approach now, if I want to do a ridge, will change. What do you now see? Okay, you added lambda high. You see that? The lambda that you added is a turning point. Does that make sense? So ridge regression work when P is greater than N. When the number of explanatory variable is more than the number of observation. And remember, you can have that kind of data in financial data. Stock. Like situation where the numbers of explanatory variable is even more than the number of observation. Of course, the ridge regression basically going to work. But you know what? The OLS will fail. Why? Why is the OLS is going to fail? It's going to fail because there will be problem of multicollinearity. Any question? Any question? You're good, right? Okay. Now, let's go to lasso now. I told you. The reason why the ridge relation is not perfect, you know why ridge relation is not perfect? Because it's still going to retain all the relevant variables in the model. And that may confuse students who cannot interpret a p-value. Does that make sense now? So because of that, we need an alternative shrinkage method that will completely eliminate the relevant variables. Does that make sense? And that's why we need lasso. Okay, that's why we need lasso. So take a look at that. That's what, so for lasso penalty, that's what we have. I think I showed you the other time. Okay, now why does the penalty matter? Now I'm talking about the lasso now and the ridge. You see what the lasso is using? The absolute value. Why the ridge relation is using the summation, of that. Okay, so they are not the same. Okay, the one, the lasso one is L1, the ridge one is L2. And of course, using L1, it's only when you use L1 that we call lasso that you will actually have the regression coefficient shrink to 0. And then when they are shrink to 0, they will be completely eliminated from the model. Okay, so that is that. Now, I think I just explained this. When lambda equal to 0, no bias. When lambda equal to infinity, no variance. When lambda equal to 0, no bias. When lambda equal to infinity, no variance. Take a look at that. And increasing your lambda increases bias. Because when you are increasing your lambda, you are eliminating a lot of variables. That is the meaning. And that we actually increase the bias, but in a way, we decrease your variance. Take a look at that. Any question? Now the question now, can we say which one is better between the lasso and the ridge? We go for lasso. Okay, you know why I'm actually going to go for lasso? Because lasso will completely eliminate irrelevant variables. It will shrink their coefficient to 0, but the ridge will not do that. Okay. Oh my God. Oh my God. This is what I said in the one when I talk about prediction versus interpretability. When you are pursuing an explanatory goal that I also call causal goal, your model will be interpretable. Okay? But when you are pursuing a prediction goal, then you need a lot of variables to make the best prediction. Therefore, difference exists between when you pursue an explanatory goal and when you pursue a predictive goal. So the larger value of lambda means more coefficient will be set to 0, like I said. So I'm not going to repeat that. Now, do you know we can actually have another module, which is another alternative, but that very module combine both lasso and the ridge. I want you to take it because of that. We're going to have two turning points, two turning parameter. Lambda 1, we go for the lasso, and the lambda 2, we go for ridge. When we have this, we call this elastic net. Has anybody heard about elastic net before? Okay, the elastic net is more or less like an improvement because you know why? Some people don't like the way lasso eliminate the irrelevant one. And some people don't like a situation where the ridge retain the relevant one. But can we play around like transiting? Let's have something that would look like a transition model. Has anybody heard about transition model? That's going to move from here to here, move back, like going from lasso to ridge, like that. There's possibility that we can We call this regime shift. In time series analysis, there's something that we call regime shifting. Okay, regime shifting. Does that make sense? So this is the idea here. Okay, so I think I've already explained it. I said both, when you want to look at ridge and the lasso now, of course, both swing coefficient towards 0. And why do they do that? To reduce the variance. Initially, when you have a lot of variables, the variance will be high, even though the bias will be low. Okay, and let me tell you this: they solve a problem, but they introduce another one. Both will induce bias. When you are eliminating variables, then you're going to induce bias. Okay, and both actually work great when the OLS fails. I think I've given you the condition under which OLS fails, when the number of observation is less than the numbers of predator. And both are computationally efficient. Okay, I think I've explained all that. Now, this is an R code. Okay, I'm going to ask my TA to walk you through this. The first one is a reach function. Take a look at that. Now I'm simulating now. Okay, now if you take a look at what I'm doing here, when I ask somebody to test a sampling property, you can play with data. Like, okay, what is the decision when the sample size is 20? What is the decision when the sample size is 50? That's a sampling property that you are testing. How sample size behave. Statistical theory has it that when sample size increases, of course, the error is basically going to go down. Okay, now take a look at what if we're going to set a seed, the same seed, because we want to simulate. We want to have the number of observations to be 500, and the explanatory variable to be 10. Okay, and because we are simulating, we already know the coefficient values. Because if I want to simulate, I need to know the regression coefficient to simulate. Now, what I'm trying to say now, if you see B, do you see B? 0.5, negative 0.5, 0.25, and I deliberately put 0, 0, 0. Take a look at that. Why do I deliberately put 0, 0, 0? I'm already saying some variables are not important. If a variable has a coefficient 0, they are not important. But do you know what I want to do? I want to test the capability of ridge and lasso. I want to see whether the lasso will be able to detect that. I want to see whether ridge will be able to detect that. Does that make sense? What we do in statistical analysis, it's just like if I ate a burger last night and I asked somebody that did not witness me when I was eating the burger, and I say, okay, can you tell me, what did I eat last night? I know what I ate last night, right? I want to know whether he can tell me. If it's a very good detector, it should be able to tell me something, even if it's not going to tell me burger, it should tell me something close to burger before I can now rely on so what I want to do right now, I already know the true state of my model. I know in my model, some predator. How many predator? One, I got 10 predator, and 6 of them as values. 4 of them, their coefficient should be 0. The one whose coefficient is 0 is assumed to be not important. Take a look at that. And I'm simulating from a normal distribution. Take a look at that. Now, let's now estimate using ridge. When you're estimating using ridge, we can set our lambda. Okay. Now take a look at that. Now, you know what I've done here. What is the true? Look at the first column. That was what I said, right? Now, the ridge, when I estimate the regression model using the ridge return this guy. When I use the conventional OLS, The conventional OLS return all those ones. Anybody? Is there anybody want to ask question? Who doesn't understand what is happening here? Is anybody? Who doesn't? Go ahead. Oh, why I choose? Oh, lambda equal to 0.1. No, I just choose that arbitrarily. I can, optimally get that from my data. But I just say, okay, let me just choose 0.1. I know if lambda equal to 0, that would favor that means OLS, right? Okay, I just start from something. So I can, just like what you said, I can try, okay, when lambda is a 0.1, when lambda is a 0 point this will happen. Okay, that's a good question. Good job. Okay, I'm gonna go back now and let you see. Okay, now the next thing, now I have this guy here. Okay, when you take a look at this guy here, Ridge does not eliminate. You can see the true, when the true value was 0, 0, what am I expecting? I'm also expecting 0, 0, right? In fact, I know the OLS will fail. Look at the OLS. The OLS is returning a value even that may even be significantly different from 0. But look at the range. You can see that even though when you look at the p-value for range, of course, those may not be significant. Okay, when I go for now, when you take a look at that now, and I decide to go for lasso for the same problem, okay, when I go for lasso, oh my God, look at lasso. Can you see that? All those ones that were 0, 0, what happened? Turn 0, 0 with a lasso. So between ridge and lasso now, so which one do you think is in agreement with reality? Is lasso? Because that automatically. So this is how we know our modeling statistics are working. They are working because we can create, if I know the true value of something, then I can actually figure it out. Oh, I got 5 more mini, right? Okay. Now take a look at that. Now, every other thing that you want to do here is what you're going to do in the lab. Okay. This time around, we have unemployment data. Okay. And we have a lot of variables. You know, the one I demonstrated, I think we have 10 variables, right? Okay. So you follow that up. Okay. Observation, like, you first partition your data, okay, into training set and test set. Yeah, I'm using 70-30 or 70 because the largest percentage of the data should be committed to training. It could be 70-30, 80-20, 75-25, and the like. Okay, what happened? What I'm doing here, okay, we have the variables, there are 5 in number. We train, we test, okay, we fit. We first start by fitting the OLS. This is what we got, fitting OLS. Okay, now the next thing is we're trying to obtain how valid is the OLS by using what we call the adjusted R square. Don't forget, can somebody remind me? Why are we using adjusted R square here? Can somebody tell me? Extra credit. Why am I using adjusted R square? Exactly. Send me a message because you can no longer, on Monday we go through module fitness and module complexity. There are 2 criteria for module fitness, the residual sum of square and the R squared. They are not going to be appropriate when you got a lot of predator in your module. Therefore, you're basically going to have a brand new criteria that consider both module fitness and module complexity, which we call the AIC, the BIC, and the adjusted R squared. Okay, now I'll take a look at what I have now. Okay, you can see, I think I don't want to rush you because you're still going to do this in the lab. I'm going to continue from here on Friday. Is there anyone who want to ask a question before I go? Anyone? Statistics is very, very interesting. It's like a story. Okay, tomorrow you're going to see again, your grade will change. Because tonight, I'll finally use the makeup. Does that make sense? So check your grade for those who actually did make up their grade with change tonight. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.